Hi everybody and welcome back. This is the Control Engineering Geek. This video presents the formulating of the MPC problem given the process model, the cost function or the index of performance, and finally the constraints on the involved variables. Let us jump into the subject. It is important to note that most of the materials that are presented in this series of videos are borrowed from the great book, Predictive Control with Constraints, which is written by MPC. The very first thing to be introduced in the formulation of the MPC problem is the process model. In this video we are going to use the state space representation. Later, I am going to illustrate how to use other type of presentations such as step or impulse responses. Using the state space technique and assuming linear process, one can model the controlled process as the following discrete time form, where x is the plant state vector with n dimension. U is the input control vector with L dimension. Y is the measured plant output vector with m sub y dimension, and finally Z is the controlled plant output vector with m sub z dimension. The matrices A, B, C sub y, and C sub z are constant matrices with appropriate dimensions. The vector Z is controlled either to track some desired reference or to satisfy some constraints or both. The Y and C vectors are usually the same, in which case, one can use the output matrix C to denote both C sub y and C sub z. This model is often generalized to include the effect of measured or unmeasured disturbances or noises. In MPC algorithm, usually we are performing the following steps. Obtain measurements, which is the output vector y of k, compute the required control action vector u of k from some computational algorithm, and inject the control vector u of k into the process. Performing these steps results in some delay between measuring the output y of k and applying the computed control vector u of k. This is reason behind not including a direct feed-through in the second equation above between the u of k and y of k. The controlled output z of k, however, could depend on the control vector u of k, which is essential for some processes such as heat exchangers with bypasses or gas turbines. The dependency on u of k and the equation of z of k will complicate the computation of u of k. But with a simple trick, just define the following. From this relation, one can see that this equation depends on the current state of the process x of k without any feed-through from the control action vector u of k. The changes to the cost function as well as the constraints are easily made, and we would see them in a different video. So, one can assume the controlled output z of k as was shown previously. Let us now jump into how to formulate the cost function or the index of performance. We need first to assume the followings. We have a linear model of our process. We are dealing with the signal L2 norms, thus we have a quadratic cost function. The imposed constraints are in linear inequality forms. The model, the cost function parameters, as well as the constraints are time invariant. We are penalizing the change in the control vector u of k rather than its actual value. And finally, through an appropriate filter or observer, we can have a good estimate of the current state of the process x of k. The notation u hat of k plus I at k denotes a future value at k plus I of the input u, which is assumed at time k. Accordingly, x hat, y hat, and z hat of k plus I at k will denote the predictions made at time k of the state, measured output as well as the controlled output at time k plus I. These predictions are made based on the assumption that some sequence of inputs u hat of k plus j at k for j varies from 0 to I minus 1 will have occurred. Based on what have been presented, we are ready to introduce the cost function. The cost that we are dealing with for now has the following form. the cost penalizes the deviation of the anticipated controlled outputs z hat from a predefined reference trajectory r. In addition to that, the cost also attempts to minimize the changes in the control actions u hat. H sub p is a window and future determines the prediction horizon. One can start penalizing the deviation of z hat from r hat from 0 or from a specific point h sub w. H sub u is the control horizon. Usually, we assume that h sub p is greater or at least equal to h sub u and thus all changes in the control prediction are 0 beyond h sub u. This means that u hat for k plus I remains constant for I equal or greater than h sub u. Now let us define the meaning of the two norms in the cost function. X transpose qx and u transpose ru are the quadratic forms which are formulated simply from the L2 norm definition of vectors as shown. The matrices Q and R are used to give different weights to the variables. Thus one can penalizes the terms differently as we can see from the following. Let the vector x have two items x1 and x2. Let also the matrix Q have the 4x4 items with values as shown. So the norm X transpose Qx can be written as, which through matrix and vector multiplications can be simplified as the following polynomial of x1 and x2. Now observe the followings. If X transpose Qx is strictly greater than 0, then Q is called a positive definite. But if X transpose Qx is equal to or greater than 0, then Q is called a semi-positive definite. One way to check the positive or semi-positive definite of a given square matrix is through the eigenvalues of the matrix. If all eigenvalues are greater than 0 then we have a positive definite matrix, and if some eigenvalues are 0 then we have a semi-positive definite matrix. If Q is the identity matrix, then we are dealing with square equations without any weights, which is simply the Euclidean norm of the vector. Next, let me introduce the gradient of X transpose Qx. Let V is given as X transpose Qx, where X is a vector of X and while Q is n by n matrix. Then the gradient of V is, where V is differentiated for each item in X. One can write the result as 2X transpose Q or as 2Qx. Three important notations need to be mentioned here. The first notation is that both weighting matrices Q and R can change along the corresponding horizons H sub P and H sub U, but usually they are kept constant along the horizons. The second notation is that an additional term can be added to the cost function as shown to penalize the deviation of the input vector from some ideal resting value u0. The last notation is as following. As HP, HU, HW, the matrices Q and R, and the reference tracking R, are free or design variables that can have any values, therefore, they can be utilized to tune the control problem here. The last part of the formulation of an MPC problem is the constraints. We can assume having three types of constraints as following. Where E, F, and G are matrices with dimensions that depend on the number of inputs, controlled outputs, as well as the values of both state and control prediction horizons. The notation vec of 0 denotes a zero-column vector, whereas vec of A, B, C transpose denotes a typical column vector. The first constraint is the actuator slew rates. The second constraint is for the actuator ranges. The last constraint, however, is for the output-controlled variables. Of course, as the controlled process requires, one can have different type of constraints such as quadratic constraint, which is basically utilized in the MPC problem to limit the propagation of some variable's norm. To illustrate how to find the involved matrices, E, F, and G in the constraints, I am going to introduce the following example. Let us have a plant that has two inputs and two controlled outputs. the control horizon is set to be 1 while the prediction horizon is 2. Let us also assume that we penalize the deviation from the first step and not from 0. Now let our problem requires the following constraints to be fulfilled at each time. Starting from the first constraint, which is on the change of the first control input. This constraint can be divided into two constraints. The first one is when delta U1 is equal to or greater than -2 as shown by the red box. By a simple trick, it can be written as minus delta U1 equal to or less than 2. Then one can rewrite the constraint as equal to or less than 0. The final step is to transform the constraint into vector matrix form as shown. Here we need to write all constraints in the form of one vector, and this is why we have added delta U2 but with 0 coefficient. Let us jump into the other part of the constraint, which is shown by the red box. Following the same steps, we can write the vector matrix form of this constraint as shown. We now need to combine both final forms of the constraint into one inequality. Do not forget to replace the delta U with delta U hat. This step is shown as, where the E matrix is simply given as. Note that, as the control horizon H sub U is 1, we have only constraints along K equal to 1. For the second constraint, which is on U2 range, you can exactly follow the steps we have used with the first constraint, and thus you can obtain the F matrix. The final set of constraints is on the controlled output, which are given as. For the first two constraints, we can use the same trick we have used with the first constraint. Thus we have. For the last constraint, we simply rearrange it as following, then we can write the constraint as vector form as. The final step would be stacking all these constraints together along the prediction horizon HP, which is 2. This step is given as. Thus, the G matrix is as shown. Now, as we are done with the formulation of the constraints, there is one point that I have to state here. In the process of solving the MPC problem, it is convenient to write down all the constraints in the term of the change of the control actions delta U hat. This step increases the efficiency of solving the online solution of the MPC. I will illustrate this step further once I introduce an example. Before jumping into the last portion of the MPC problem, which is the prediction based on the given plant model, I would like to introduce the effect of computation time delay on the MPC problem. As the MPC controller is an online controller, which means that the MPC problem requires some time to be solved in between the samplings, therefore, this time delay should be accounted for in the MPC problem. The following figure illustrates how this computation delay is handled. First, let us assume that both the measurement interval and control update interval are the same with length of Ts. The process output is measured as kTs, which is labeled as y of k. If the process is subjected to a measured disturbance, then it is also assumed that the measurement of the disturbance is done at the same time of kTs and is labeled as dm of k. Let tau be the time taken by the MPC to predict the control action sequence. The first item in this sequence is u of k. The input signal u of k is assumed to be held constant until it is recomputed Ts time units later. This sequence is repeated at time k plus 1 all multiplied by Ts, and regularly therefore. So, one can notice a time delay of tau between the sampling of the process states and injection of the computed control action. Now, let us suppose that a linear and continuous model of the controlled plant be given as. Here it is enough to consider the measured outputs y, where the controlled outputs z is treated in the exact way. From the figure, one can see that y of k is equal to yc of kTs, and that the control signal uc of k is equal to u of k, which is true in the shown interval. So, the process can be simulated over all times by. Solution of this state space is given by the following expression, where t sub 0 which is less than t is the initial time, whereas xc of t0 is the initial state. Now, if we apply this solution over the interval shown as side, we can get the shown solution to the left where we have defined that x of k as xc of kts. Using change of variables is zeta equal to kts plus tau minus theta, it would be easy to show that. Here gamma 1 is a constant matrix and the corresponding equation above can be written as. Following the similar steps but with the other interval, we can have the following relations. In the last expression, we have defined the followings. For our final expression of x of k plus 1, the form is not in a standard discrete state space representation because of the presence of u of k minus 1. However, one can easily transfer it into the standard format by introducing the following change of variables. And the resulted discrete state space dynamic would be, where a hat and b hat are given as, whereas the output in term of the new variables is, where c hat is. By the simple steps, one can include the MPC computation time into the considerations. Now, as we have introduced modeling, cost function and constraints, the last ring in the MPC problem series would be the prediction. First we have utilized a standard discrete state space as shown to represent the controlled process. To predict the future states x hat using the prediction of future control actions u hat, we simply use the model above repeatedly as following. At time k, the prediction of x for time k plus 1 is, whereas the prediction of the x at time k plus 2 is, whereby using the expression above, we can write. And from here, you can see where the equations can go. So, at time k plus h sub p is just the repeated applications of the model above hp times. Recall that it was assumed that the input u will only change at times 1 to k plus hu minus 1, and will remain constant after that. So we have u hat of k plus I at k is constant between hu and hp minus 1. As we have stated earlier that the MPC will be expressed in the term of delta u hat, so it is convenient here to express the predictions above in term of delta hat. This can be done as we have u hat of k at k as, and u hat of k plus 1 at k as, and all the way down to the u hat of k plus hu minus 1 at time k. Thus we can have the new prediction forms as x hat of k plus 1 at k, x hat of k plus 2 at k, where the last term is just u hat of k plus 1 at k. This can be simplified even more as, you can follow the pattern above for x hat of k plus hu at k. For state predictions beyond the control horizon hu, we have, and for a time k plus hp at k. Now we can stack all previous state prediction into vector and matrix expression. The state prediction vector is, which is equal to the following matrix multiplied by the estimated or real state of the plant at time k. The following is the matrix associated to the previous applied control action at time k minus 1. All right-hand side for now is for past information. This expression is added to the following matrix which represents the coefficient of the future predicted control sequence. This was the state prediction. For the controlled output prediction z hat, we can simply use the dynamic of the controlled output z as following. At time k plus 1 at k, we have the shown relation, where we can easily extend it to time k plus 2 and all the way to the time k plus hp. Or we simply multiply the state prediction equation with a diagonal matrix with c sub z as the diagonal items. This was the presentation to how to use the process model for prediction. it is important to state the following. As we have the prediction expression, we are dealing with a to the power I as it is indicated by the red boxes. The power I can have a quite large value. This can lead to numerical problems, especially when the plant is unstable. Thus, the safest way to predict the states for long horizons is, probably, to iterate one step at a time. We have come to the end of the video. I was planning to include an example about the paper machine head box at the end, but this may make the video to be very long and boring to some of us. Thus, I postponed the example presentation for the next video, so stay tuned. Thanks again for watching this video, and please do not forget to hit the subscribe button and activate the ring button as well. See you soon, hopefully.